All right, so 6.1, discrete random variables. All right, a random variable is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. All right, they're usually denoted by using, typically denoted by using capital letters. All right, so a discrete random variable has either a finite or countable number of values. I'll give you guys a chance to write it down. All right, so it can be plotted on a number line with space in between each point. So in other words, if it's, it says it's countable or finite. So in other words, if it's four, it's four. There's no number in between. It's just four. And you'll see what I mean when we get to our examples. No, there's no estimation. There's no measurement involved. It's just that number. So that was discrete random variable. Then we have a continuous random variable. That's a little different. So that has infinitely many values. And that can be plotted on a line in an interrupted fashion. So like I said, when we see the examples, you see a clear-cut difference between the two. All right, so first exercise, discrete or continuous. Is anybody still copying this top? Well, I don't need to go that high. So the number of A's earned in a section of statistics with 15 students enrolled. So that would be a discrete random variable because it's countable, it's fixed, if 14 people earned the A, then 14 people earned the A, and there's no discrepancy in that. It's a countable number, and like I said, it's fixed. So no such thing as 0.5 of a person, or you halfway made an A. You either made an A or you didn't. Now, the weight of a sandwich at the deli would be continuous. Reason being is because your measurement, any type of measurement, is seen as being continuous. Because let's say if it weighs at 1.5 grams, if you have a more accurate scale, you could have 1.57 or 1.5761. If you have a scale, your scale could be more accurate than my scale, and both answers are still considered correct. So measurement most definitely will be an example of something that is considered continuous random variable. All right. Next one, the number of cars that pass through a McDonald's drive-through in the next hour. That would be discrete. Four cars either pass through the McDonald's drive-through, or four cars, or it's 5 cars, or it's 10 cars. So that's a number that's countable, and that's why it's considered discrete. There's no such thing as a third of a car that passes through the McDonald's drive-through. Any questions? Any questions? And then the last one, the speed of a car that passes a state trooper, that will be considered continuous, because once again, it's measurement, and somebody's gun could be, what are they called? Can't even think of the name. Somebody's gun, I'd say it like that, could be more accurate than the next person. So that's why that's considered continuous. Any questions on either one of those? Excuse me. All right, pulling up. All right, probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. All right, so rules for discrete probability distribution, and I believe we talked about these rules in chapter 5 as well. So adding up all your probabilities, they have to equal to 1, and this was the symbolism that he gave, but that's what it means. All probabilities add up to 1. Add all probabilities equal to 1. And then each one of your probabilities, is in between 1 and 0. Those are your rules for your discrete probability distribution. If they don't fit that, then it's not considered a discrete probability distribution. All right, we're done with the blue. All right, so they give us these three charts and ask us which of the following is a discrete probability distribution. So I'll give you a chance to write those down.
Can you go back up just a little bit for the blue? Thanks. Okay, I'm good. Thank you.
So here in the green, we're looking at which of the following is a discrete probability distribution. So we have 0.2 or 0.20, 0.35, 0.12, 0.40, then negative 0.07. The next one is 0.20, 0.25, 0.10, 0.14, 0.49. Then in that third one, got 0.20, 0.25, 0.10, 0.14, 0.31. So, like I said, I'll give you a chance to write that down. All right, so looking at the first one, it doesn't fit the discrete probability distribution rule because rules. It fails rule 2. Remember that your probabilities, each one of your probabilities, need to be in between 0 and 1. B fails rule 1 because they need to add up to give you 1. And if you add those up, it gives you 1.18. So when you add up your probabilities, can't be less than 1, can't be greater than 1. It's supposed to be exactly 1. All right. So looking at C, it passes, when you look at it, initially you see that each one of them are in between 0 and 1. So it passes, if it passes rule 2, and then if you add them up, they end up equaling to 1 itself. So it does represent a discrete probability distribution because it satisfies both rules. All right, any questions? Any questions on that? All right, can we scroll up? Everybody good? All right. So now this last thing before we go to 6.2, if my math lab asks for the mean of a discrete random variable or the standard deviation of a discrete random variable, it's like, I don't know if you remember before, I asked you to use a website app or calculator to find it. Just do the same thing for those. I'm not going to hold you to the process to finding those. If you Google, mean of discrete random variable or standard deviation of discrete random variable, it'll give you plenty of websites that all they're going to ask for is for you to type in the data values and hit enter. So, yeah, that's all I'm going to need from you on that. Just find something or have something reliable that can calculate that for you. I know they mentioned it at the tail end of the section. So I'm not sure if I forgot whether I put any of my math lab problems on it, but like I said, just find app, website, or calculator that can calculate that for you. If you have any problems, always feel free to ask. All right. Questions on anything out of 6.1? All right, and I know some questions may not show up until you get in there, so that's understandable. All right, let's look at 6.2. Remember, chapter 6 is only 2 sections, 6.1, 6.2. So we have the binomial probability distribution. So binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive outcomes. All right, I'll stay right there for a second. But these two outcomes are generally referred to as success and failure. Give you a chance to write before I scroll up. All right, so these two outcomes are generally referred to as success and failure. So in basketball, as an example, success will be making a shot, failure will be missing a shot. So notice they're mutually exclusive. You can't make a shot and miss the shot at the same time. So, it's either you made the shot or you missed a shot. So that's where the binomial, is two, binomial probability comes into play. That's why it's called binomial. You only have two options, success and failure. The experiments in which only two outcomes are possible are referred to as the binomial experiments, provided that certain criteria are met. Of course, we're going to talk about those of that criteria. All right. Criteria for a binomial experiment. So an experiment is said to be a binomial experiment if the experiment is performed a fixed number of times, each repetition of the experiment is called a trial. So we have four, I believe. Yep, we have four of them. All right, we good with the black. Still, okay, I see a thumbs up. Appreciate that. Okay, second criteria, the trials are independent. Third, for each trial, there are two mutually exclusive outcomes. Remember, we just mentioned success or failure. And we got one more. Of course, I'll give you a chance to write. right, and the fourth criteria, the probability of success is going to be the same for each trial of the experiment. All right, so let's see if you copy me. All right, so notation used in the binomial probability distribution. Don't want to scroll up too far. Somebody's. All right. So lowercase n is the number of trials of the experiment. Lowercase p is the probability of success. 1 minus p is the probability of failure. All right, how are we looking on 4? Let's scroll up. Okay, and then the number of successes in trials will be x. And notice x can be, well, will be in between 0 and 0 and n inclusive. It can be equal to 0 or n. We'll talk about what these numbers mean in a second, in these letters. All right. Got it done with the green. Okay, so the directions for the next exercise: determine which of the following probability experiments qualify as binomial experiments. For those that are binomial experiments, identify the number of trials, probability of success, probability of failure, and the possible values of x. So first we need to see if it fits the criteria. We have our 4 criteria that we have to meet. And then if it does meet that, we want to identify the number of trials, probability of success, probability of failure, and possible values of x. All right, so the first one, An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. All right, can I scroll up? Okay, so we're going to run through the 4 criteria first. So the first one, is there a fixed number of trials? So the answer is yes. So they asked him or they asked her to shoot 3 free throws. So it's fixed number of trials. Are the trials independent? The answer is yes. Shooting one shot has nothing to do with the person shooting another shot. So they are independent of each other. Are the events mutually exclusive? The answer is yes, because you cannot miss and make the shot at the same time. So that means those events don't coincide. It's impossible to miss and make the shot. You either miss it or make it. So that's what it means by being mutually exclusive. They don't have any event that can occur that is in common. And is the probability of success the same for each shot? The answer is yes. This person is an 80% free throw shooter. Missing one shot is not going to change that person's percentage, historic percentage. So if all throughout his or her career, he or she was 80% free throw shooter, missing a shot doesn't change that. Still an 80% chance that that person is going to make the shot. All right. Questions before we go to the next part of this problem. So remember, the first thing we need to do was establish that it is a probability distribution experiment, binomial probability distribution experiment. It has to meet those 4 criteria. And then after that, we have to establish, well, that's in the green, it is a binomial experiment because it meets all 4 criteria. So now we have to establish our variables. So n is going to be 3/4. That's the number of trials. Probability of success, 80%. So that's 0.8. That's the person making the shot. Probability of failure, 1 minus p. So that's going to be 0.2. In other words, 20%. And then x is going to be 0 to n. So that's 0 to 3. So 0 means that the person missed all 3 shots. 1 means that the person make 1 shot. 2, make 2 of the shots. And then 3, make all 3 of the shots or her shots. So your x is always going from 0 to n. Whatever the number of trials are, that's going to be the last number that x could possibly be. And 0 is always going to be the first number that x could possibly be. All right, any questions, any questions? All right, so let's look at the next one. Probability experiment in which 3 cards are drawn from the deck without replacement and the number of aces is recorded. All right, so let's go through our criteria. Is it performed a fixed number of times? The answer is yes. You're going to pull a card three different times, so that's the number of trials, 3. Are the trials independent? The answer is no, because it says without replacement. So in other words, you're not putting the card back. That means you're going to affect the probability of the next card being drawn. Because remember, initially you're going to have 52 cards in your deck. You pull one card out. Now you have 51 cards in the deck, which is going to affect the probability. So the trials are not independent. One card being pulled will affect the probability of the next card getting pulled. So it is not a binomial experiment because it does not meet all the criteria. Any questions? All right. One more just to make sure we're good. Am I still holding on? Am I good? So, according to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. All right. So, all the experiments performed a fixed number of times. The answer is yes. Got 10. Choosing 10 people. Are the trials independent? The answer is yes. Me choosing somebody has nothing to do with me choosing the next person. You know, it doesn't change the probability there. Are the trials mutually exclusive? The answer is yes. So somebody being a chocolate lover has nothing to do with the next person being a chocolate lover or vice versa. Probabilities of success is the same for each. The answer is yes. So it's either 28, I mean, it's going to be a 28% chance because it's based on the population poll. I believe it was Americans, right? Yep, 28% of Americans. So that probability will be the same. So this experiment is a binomial probability experiment because it meets each of the criteria. All right. Any questions? Any questions? Everybody good? Cool, cool, cool. So now that we've established that it does fit the binomial probability experiment criteria, go ahead and establish our variables. Number of trials, 10. That's N. 28% success. So don't forget to convert that to a decimal is 0.28. Probability that there's a failure. Now, success means choosing someone that says that chocolate is their favorite flavor. Failure is choosing someone that doesn't say chocolate is their favorite flavor. So a 72% chance that that could occur. And then X is going to be 0 to N. So that's 0 to 10. 0 means meaning that out of the 10 people you chose as a sample, no one chose chocolate as their favorite flavor. 10 means that out of the 10 people you chose, all 10 of them chose chocolate as their favorite flavor. All right. Very good. Before we look at the next thing. All right. So the binomial probability distribution function. We have the probability of X. Let's see. When X is going to represent the number of successes, we already established that. N is the number of trials, and P is the probability of success. We have NCX, and then we have P to the X power. I wrote those X's in red, the numbers in red, to signify that those are actually exponents. So we have P to the X power here, and then we have 1 minus, oh, hold on now, where my stuff go? There we go. Sorry about that. And then we have 1 minus P to the N minus X power. All right. So now this C right here is actually the combination function. So that is in your calculator, the scientific calculators. Now I'm going to show you how you can walk through the formula, but also you could Google binomial probability distribution calculator. And there is one good one out there that, all you do is put the numbers out in there and it calculates the probability for you. So we'll show you in a second, but this is the formula. And once again, C is not something that we're going to substitute a number in for. C is your combination function. All right. Still see writing, so we'll wait a second. All right. So let's try to put this to work. It says according to the CTIA, 41% of all U.S. households are wireless only households. That means no landlines. In a random sample of 20 households, what's the probability that exactly 5 are wireless only? So A is the first one. We're going to look at the probability that out of, you chose 20 households, exactly 5 of them will be wireless only. right. So first thing we want to do is establish our variables. So success is 41%. You're talking about choosing a household that is wireless only, 41% chance. Failure, 1 minus that 0.41, which is 59%. Number of trials, which is 20. And X goes from 0 to 20. Remember, X always goes from 0 to N. 0 means out of the 20, you didn't find any that were wireless only. 20 means that everyone you chose, every household you chose, was a wireless only household. All right. So then you put that in the formula. You want to know what's the probability of exactly 5 are wireless only. So the probability of 5. So that's 20C5. Remember, we're just following the formula, right? That's up here. So 20C5, that's 0.41 raised to the 5th power. 1 minus 0.41 raised to the 20 minus 5. So it depends on your calculator. If you have the calculator where you can put the parentheses in, raise things to the power, and I'm not talking about, it doesn't have to be a graphing TI 80 something calculator. It can be just a regular scientific calculator. If you can put it in your calculator just like this, then you don't have to do any work. You just put it in there. You would have to do this though. It just depends on your calculator. You may have to use this symbol in order to raise it to the exponent. But that's something that I can work out with you, after class or in an office hour. We can look at your calculator, see what kind of function you have in your calculator. But if not, you have to do it in pieces. 20 minus 5 will give you 15 right here. 1 minus 0.41 will be that's 0.59, and you'd have to do things in pieces. So, but when you do that calculation, you'll get 0.0656 or 6.56%, whichever way my math lab want the answer. And then, so one way this could be worded as far as your conclusion, in 100 trials, if this study, and basically, let me say it like this, in 100 trials of this study, we would expect about 7 trials to result in 5 households that are wireless only. So that 7 comes from this 100 being multiplied to that 0.0656. And we talked about that before. When they give you that number, 100 trials, you multiply it to that probability that you had. So you're talking about this number right here. And so when you say in 100 trials, that means if we survey 20 households 100 different times, All right. Questions on anything so far? Make sure we're good. All right, can we go to B? Is anybody still copying? All right. So B is fewer than 3 are wireless only. So when you choose 20 households, what's the probability of getting fewer than 3 that are wireless only? So if you're talking about fewer than 3, you're talking about 0, 1, or 2. So what we would do here is find the probability of getting 0, find the probability of getting 1, find the probability of getting exactly 2, and then add them together. Anybody still copying that red? Anybody? All right, I see no head shaking, so that's good. So, and that's what I did right here. Just ran out of room as far as moving right to left. So the first one is the probability you know, how you would plug it in for the probability of getting 0. Second one down here is the probability of getting 1. And then here, the probability of getting 2. Once again, these are things you would plug into your calculator. So I didn't do this in my head or anything like that. So once again, if you need help with how to use your calculator, once you get to this assignment, make sure you get with me so we can make sure you're straight. Also, once again, there is a, I don't know what the website is, but when you Google the binomial probability experiment calculator, it's like one of the first ones that pop up, and all they ask you for is n, x, and p. Put it in there, and then these values will come out. So for the first one, 0.000026, next one, 0.000363, and then for the probability of 2, 0.002397. Add those together, and you get 0.0028. All right, any questions, any questions? All right, so the next one, C, it says at least 3 are wireless only. So when you talk about at least 3, that means 3 is the least of your values. And then you're talking about 3 all the way to 20. All right. So now what you don't want to do is have to calculate the probability of 3, probability of 4, probability of 5, all the way to 20, like we just did 0, 1, and 2. But what we can do is use the complement rule here. So if we know the probability of 0, 1, and 2, but we want to know the probability of 3 all the way to 20, I can subtract the probability of 0, 1, and 2, which is what we just found at 0.0028. Because remember, the complement is everything else. So we wanted 3 up to 20. So I can subtract 0.0028 from 1, and that probability will be 0.9972. All right, problems, any problems? All right, I think this is the last one out of these examples. So indeed, we want to find the probability of getting the number of households that are wireless only between 7 and 1 inclusive. So that means we're including, I said 7 and 1, 5 and 7 inclusive. So that means we're including 5 and 7 as a part of the probability that we want to find. So that would be 5 or 6 or 7. So this one is similar to when we had 0, 1, and 2. Just need to find the probabilities of 5, 6, and 7 individually, plug them into the formula, and then calculate them. So that's what we have here. and we add them together. That'll give us 0.3381. All right, questions. All right. Yep, thought so. So that's it for 6-2. So, yep. This is just something somebody else asked. But so that third test is 5.1 through 5.4, and then 6.1 and 6.2. All right. So next class, I'll do like I did before. I'll set aside for you guys to ask whatever questions you want to ask. And so that's going to be Wednesday, right? So ask whatever question you want, whether it be from test 1, test 2, or test 3, all those chapters, 1 through 6. And then on Monday, we will get into chapter 7. So we only have, let's see, after this week, we have 2 weeks left. And that first week in May, will be over. So this thing moves quick. So questions on anything? Anybody try anything, get stuck?
I have a question.
Yep.
Is the third test still over Zoom, or do we do that on our own?
Well, what I probably would do, since this is an 8-week class, I'll probably just let you do that on your own and let the final test just be through Zoom, be proctored through Zoom. So that's probably how we'll flow.
Okay,
Yeah.
and will that be like on a scheduled Zoom or like the last Zoom?
Looking at, let me see, this class ends on, let's say May 7th. Well, I don't say May 10th, and this says May 7th. So we would do, that first week of May. So I'm looking at probably Wednesday. So that's May 5th. May 5th would be our last class date. So we can either do it, and it's up to you guys. We can either do it on that Monday, which is May 3rd, or no, it'll probably be best. No, we'll just do it May 5th. That's Wednesday. Just May 5th is Wednesday. That's our last day. We can extend it out, and we'll do our final exam on that day. And then also all of your assignments will be due. I think I already have it set for May 7th. So all of your assignments will be due May 7th. Yeah.
Okay, thank you.
Yep, not a problem. So
Oh, actually, is the test for chapter 7 and 8, is that our final exam, or is there a whole nother final exam?
Well, the way it's supposed to work is 7-8 is going to be a separate test. That'll be your fourth test, and then there's a separate final exam. Let me think about it though. That might be our final test, and that might, I might just make that a final exam. So.
Okay, thank you.
Yeah. I most definitely have an answer for you, you guys, by next week on that one. All right. Anything else? Anybody else? Pretty good. All right. So once again, next class set up for you guys to ask whatever questions you want. So make sure you look into, get into my math lab, see if you get stuck on anything, bring it to class, and we'll hash it out. If you feel like you don't really have any questions, then I'm not going to hold you hostage or make you come to class. Just make sure you get your work done. Make sure you get the work done. And don't forget, any scratch work for any test, you should be shooting that to me in an email. You don't have to write out word problems or anything like that, but any work that, call for any type of calculation or scratch work, make sure you send that to me. And if you guys are good,
We're
I'm
supposed to
good.
send scratch work for every test? We're supposed to send scratch work for every test?
Yeah, if it called for it. Now, I know in chapter 1 and 2, it may not have called for much, because I know it was a lot of definitions and graphs. But like chapter 3, you know, like mean, mode, and median, and different things like that, you know. But if it didn't call for much, then just send me what you had.
Okay, so if we like don't have any anymore, because I didn't know.
Fail
Like
the class.
executive points.
Fail the class. No. Then just make sure from this point forward that you get it to me. It's all good.
Okay, I'll look for it, but I don't know if I still have it, but I'll do it for the next test.
Yeah, it's all good. Yeah, just shoot it to me the next test. It'll be fine. Yep. All right. Anything else? Anybody else? Everybody good? All right. So like I said, you know, this thing rolls. So make sure you guys stay on top of it. And I'll see you guys on next class. Y'all have a good one.